So we'll talk about celestial coordinates, but first we'll talk about Earth's seasons, which all have to do with the motion of the Earth around the sun, which the ancients saw, of course, as the motion of the sun around the Earth. We still think of the sun as moving through the celestial sphere, but you got to remember the celestial sphere is just a coordinate system. We don't think the sun's really moving. It's just moving through the coordinate system, just like you can make any plot, a graph. You can make a graph of a line or something, and something moving up and down on the graph doesn't mean that there's literal motion. So it's a depiction of the celestial sphere. Earth's spin axis is actually tilted with respect to its orbital axis around the sun. So what we have here is Earth's actual spin axis, but there's a tilted plane here which represents the motion of the sun through the celestial sphere. And the tilt of that plane, which is this reddish thing called the ecliptic, is because Earth's spin axis is tilted by 23.5 degrees with respect to the axis of its orbit around the sun. So those two axes are not actually perpendicular. If they were, we actually wouldn't have seasonal variation. Because with the tilt of the axis the way it is, it actually changes the relative altitude of the sun over the horizon as we move through the year. I actually don't particularly like this diagram for demonstrating this feature, so we have the ecliptic, but I'm actually going to, well, this is another way of looking at it. Okay, so the celestial sphere again, but this time we're actually introducing a coordinate system. I mentioned that there's a coordinate system that acts like latitude and longitude on Earth, which is used to indicate the locations of stars on the celestial sphere. The equivalent of earthly latitude is this declination, which actually goes from 0 at the celestial equator down to -90, which again is like latitude on the Earth. And we go up to +90 at the North Celestial Pole. So if you look at Polaris, it has a declination of around very close to +90 degrees. And if we look at, say, Pisces, or one of the constellations along the celestial equator, that would have a declination of about 0, because the celestial equator is like the equator on Earth, has a declination, or latitude, if you will, of 0. But we're not done yet, because we need to have something that's analogous to longitude. We need to have that east-west coordinate. Now, the whole point of this is that the coordinate system spins with the stars. So we want to have a coordinate system set up so that if we indicate the location of a star, everybody can find it based on the time, the current time of day. You would know how this whole sphere is supposed to rotate to give you its orientation now, because it spins every 24 hours, right? So at a moment in time, if I say, well, let's look at a star that's at 0 declination and 2 hours right ascension over here, you would probably use a computer these days to get your celestial sphere oriented according to its daily rotation, and then you know exactly what direction in the actual sky that point was, because it's moving all the time. Because that point, is participating in the rising and setting of everything in the celestial sphere. Okay, so unlike longitude on Earth, we use time units for the right ascension coordinate. And the reason for that is because we know that this whole thing spins every 24 hours. So we actually use hour units, so that two objects that are 1 hour apart in right ascension we'll see one object be replaced by the other if you keep looking in a given direction. They'll track each other through that point, and it'll take exactly the number of hours. That's the difference between their right ascension coordinates. So if we have a point here on the celestial equator and another point on the exact opposite side, and we stare at this point in the sky somewhere up there, it would take exactly 12 hours for the star we started looking at to be replaced by this new star that would slowly slide into the field of view 12 hours later. Okay, so it's 24 hours of time. It's not exactly normal clock time. It's not exactly time according to a solar clock like what we have in the back of the room. We actually have to use a different kind of time. We have to use sidereal time because we're interested in the spin of the stars. And the spin of the stars is actually not exactly 24 of our normal hours. It's a little bit less time than that. And you can actually tell that if you think about this thing called the ecliptic here. The sun moves along that ecliptic. Well, if the sun's rate of diurnal motion was exactly the same as the stars, it wouldn't move along the ecliptic. It would actually stay fixed like any other star. So that's actually the reason that we have two different kinds of time that we're dealing with in astronomy that are pretty similar, but slightly different. Okay, so this is a diagram that I think does a better job of explaining where the seasons are actually coming from. Because in this diagram, we have the orbital plane of the Earth flattened out. I like to look at it that way. I think of that as the flat plane. And then relative to this plane of Earth's orbit around the sun, you have a tilt of Earth's spin axis by 23.5 degrees. So these are just, obviously, the Earth at 4 different points evenly distributed around the year. And this light sort of cyan dashed line is the celestial equator. And then, of course, we also have the spin axis, which gives us the north celestial pole at the top, south celestial pole at the bottom. All right, so the point of this diagram is that because of the tilt, because this axis is not exactly vertical, right, that means that the sun is going to achieve different levels above the horizon during the year. And we can actually see that pretty easily if we think about standing. Let's just suppose we're at the North Pole. If you're at the North Pole, then the celestial equator actually describes your horizon. You can never see below the celestial equator if you're on the North Pole, because if you try to look below the celestial equator in the sky, you'll just be looking at the ground. Okay, that actually comprises the horizon if you're at the North Pole. Okay, so if you're at the North Pole, and it's this time of the year, we would actually call this winter in the Northern Hemisphere. Well, what are you going to see? You're going to see the sun coming in below this dashed line. So you've got to imagine this dashed line going farther out into space. And the sun is below that line that I'm indicating. Well, actually, if you're at the North Pole, it means you're not going to see the sun at all. It's not just going to be low in the sky. It won't even rise, which is why you have total darkness at the North Pole for a few months of the year. As we get, remember the Earth is moving counterclockwise around the sun. So if we get down here, which is around the spring equinox in March, what we're going to see now is the sun actually in the celestial equator. And then over here in mid-June, we're going to see the sun above the celestial equator in the sky. Even at the North Pole, it'll be above the celestial equator. So it will have risen. Even at the North Pole, you'll have some sunlight to warm you up. But it won't be very direct sunlight because it'll only be about 23 degrees above the horizon because of that tilt angle. Only 23 degrees. There's never any high noon at the North Pole on Earth. The sun is never exactly overhead or even close to that North Pole. So it's the tilt of the axis that gives rise to these seasons. If the axis weren't tilted, then every day on the North Pole would be like every other day. And if there were actually zero tilt, what that would mean is that the sun would always be right on the horizon. It would never rise and set. It would just keep hovering on the horizon, drifting around in a circle around you every 24 hours. And the same would actually occur at the South Pole. So the tilt is what gives us the seasons.